Okay guys, let's pick up where we left off in 4.5. This is the u substitution portion of integration. So let's pick up some of these more complicated ones. Again, I have the integral of negative 4x over 1 minus 2x squared, quantity squared. So again, the thing that's on the inside that has more complicated stuff going on is this 1 minus 2x squared. And that means the du here is the derivative of this, which is negative 4x dx in this case, which means my entire numerator becomes my du, and this is over u squared, because my inside is my u, which we would normally call u to the negative second du. When I integrate that, be careful, going up 1 from a negative power really makes it look like a smaller number. This becomes u to the negative first over negative 1 plus c, or negative u to the negative first plus c, which we might call negative 1 over u plus c. Now what is u originally? The 1 minus 2x squared. So this is negative 1 over 1 minus 2x squared plus c. And good news, this also applies to trig functions. We have cosine squared x, sine x. Now, the thing has multiple things going on is really this cosine squared. If you let u equal cosine x, then du is actually negative sine x dx. Now, what that means is that I only have a sine x dx, so if I multiply by negative 1, negative du equals sine x dx. Which means this turns into u squared times negative du. I can move the negative out front, negative u squared du, integrate. So we have negative u cubed over 3 plus c. Add 1 to the power, divide by the new power. Now what was u originally? Cosine x, so this was negative. You can bring the 1/3 out front, or you can leave it underneath. Cosine cubed x plus c. And again, what can you always do to check if this is right? You can take the derivative of your answer and see if you get back to the original. Now, when you're using u substitution with these indefinite integrals, you always go back to x. You have no real other choice. But when you have definite integrals, you can either go back to x and evaluate at those points, or you can look at what your bounds are in terms of x and convert them into bounds for u so that you don't have to go back. And so I'll show you what that means here in this next problem. Integrate the integral from 0 to 1 of x times x squared plus 1 cubed dx in 2 different ways. So the first way I'm going to do is when we go back to x like we've been doing the last ones. We let u equal x squared plus 1. Then du equals 2x dx. I only have an x dx, which means du over 2 equals x dx. Now if we convert this integral, what I like to do if I'm going to go back to x is instead of writing my bounds of 0 to 1, those were in terms of x. So I will write x equals 0 to x equals 1 to remind myself that those bounds are in terms of x. And then this becomes u cubed times du over 2. So this is 1/2 times the integral from x equals 0 to x equals 1 of u cubed du. When you integrate that, that's u to the 4th over 4 times 1/2. So that's 1/8 u to the 4th. Evaluated technically from x equals 0 to x equals 1. And by that I mean I take my u back to x. So this is 1/8 times x squared plus 1 to the 4th. Evaluated from 0 to 1, and now I can just plug in 1 and 0 respectively. 1 squared is 1, plus 1 is 2. 2 to the 4th is 16, so this will be 1/8 times 16 minus, when I plug in 0 I get 1 to the 4th, so minus 1/8. So this would be 16/8 minus 1/8, which is 15/8. Now, how would this look if we had changed the bounds? I do everything exactly the same. U equals x squared plus 1. Du equals 2x dx, which means du over 2 equals x dx. But what I do is when I make this equation, I recognize that if x equals 0 and x equals 1 are my bound, I can plug them both into this equation to get what my bounds are for u. So that means my lower bound of 0 is now u equals 0 squared plus 1, which is 1, and u equals 1 squared plus 1, which is 2, which changes my bounds for u to 1 to 2. That way, when I integrate it, the same integral, I now have 1/8 u to the 4th. It's now from 1 to 2 because I was allowed to evaluate it in terms of u. Now, what do you notice when you plug in 2 or 1 here? 2 to the 4th is 16, so it's 1/8 times 16 minus 1/8 times 1, so it's that same 16 over 8 minus 1 over 8, which is 15 over 8. So what you notice is that no matter which way you do this, it works just fine. Now, if you prefer to go back to x before evaluating, that's okay. If you prefer to convert your bounds, that's okay too. You're trading work in one way for work in another. So either way is fine when you're doing definite integrals and you need to use u substitution. One last thing from this section that is somewhat important is that integration can occasionally be difficult, and sometimes you can simplify the evaluation of a definite integral over an interval, particularly if there's a level of symmetry about the y-axis, particularly if your functions are even or odd. Now, the things we know about even functions is they are same on the left and the right side of the y-axis because f of x equals f of negative x. That means the area under, like the integral, which varies the, your displacement or your area under the curve, will be exactly the same on the left and the right side. So instead of going from bounds negative a to a, you can double it and instead go from 0 to a. And that is sometimes helpful because 0 is a lot easier to plug in by comparison. Now, odd functions, that the area on the right side of the y-axis is always the opposite of the area on the left side of the y-axis, which means that if you have an integral from negative a to a of an odd function, there's an equal amount of area above the axis, the x-axis, and an equal amount below it, and those two areas will offset, producing an integral of 0. So integrate the following functions. The integral from negative pi over 4 to pi over 4 of cosine of 2x. One thing to remember is cosine x is even, so this should be 2 times the integral from 0 to pi over 4 of cosine 2x dx. Now this is kind of a u substitution. If u is 2x, then du equals 2 dx. Convenient, I don't have a 2 on the inside, but I can take my 2 and move it to the inside, the one that I got from doubling. And then this turns into the integral from, okay, so if u is 2x, if x is 0, u is still 0, but if x is pi over 4, 2 times pi over 4 is pi over 2. So I'm going to do this in terms of u. The integral from 0 to pi over 2 of cosine u du, and that integral should be the sine of u, evaluated from 0 to pi over 2. So it's the sine of pi over 2 minus the sine of 0, which is 1 minus 0. So this gives me an area of 1. Lastly here, the integral from negative pi over 2 to pi over 2 of sine cubed x cosine x. Okay, so let's talk about, is this even or odd? And then the question becomes, sine is odd, cosine is even. What happens if you take an odd times an even? Well, think about odd functions times even. Think x cubed is odd, x squared is even. What happens when you multiply them? You get x to the 5th, which is odd. So generally speaking, this is odd times even, so the product is odd. So this whole function is odd. And what do we know about odd functions? If they have identical bounds on either side of 0, this integral has to equal 0. So even if it's something, we could use u cubed and go from there. But we know if the function is odd, that the integral, as long as these bounds are the same numbers but negative and positive, is 0. And this is really all there is in chapter 4 in this section 4.5.